Hello everyone, welcome to the lecture number 32 of NPTEL lecture series on charge infrastructure. In this lecture we will see full bridge based DC-DC converter, obviously isolated DC-DC converter. In this case so we have been discussing about the different isolated DC-DC converter. In that we have seen our forward converter. We have also seen various configuration of forward converter. We have seen forward converter with demagnetizing winding, and we have seen dual switch forward converter, and we have understood what are the advantages and disadvantages of forward converter. Then we moved ahead and see the push pull converter. In the push pull converter we have seen how we can fully utilize the core by making sure the flux in the core goes from minus phi m to plus phi m value. That means we can go in two quadrant, I mean the fluxes in going in a positive direction or in a negative direction. That's when we can ensure that we can utilize our core fully. That means we can allow the flux to go from minus B max, or flux density to go from minus B max to plus B max. Here in this case we have only allowed goes from 0 to B max value, while here in this case we went from minus B max to B max value, and that for the same voltage, number of turns and frequency, our area of core gets reduced by half. That means we can say we are fully utilizing the core. Now we have seen different disadvantages also with this push pull converter, like voltage kickback issue due to the leakage inductance of these windings, that also we have seen. And then we have seen that the switches has to be sized for the twice the voltage rating. So that those were the some of the disadvantages we have seen with the push pull converter. And then let us move ahead in discussing the other DC-DC converter, and most specifically the full bridge DC-DC converter, or you can say full bridge converter. Commonly it is used as a full bridge converter. Now in full bridge converter, if we look very carefully, in full bridge we are using two half bridges. Here we have made our switch with MOSFET. One can also use with IGBT with the body diode also we can make. But here we have the usage of MOSFET has some advantage. We will see that as we go along in this lecture, and the next over subsequent lectures we will see. We use the MOSFET so that we can go for very high frequencies, and because of that we will have some advantages. We can utilize some of the good advantages of this converter. So now let us see a simple operation. Since we have 4 switches, we can modulate them in a different manners. So we will see the first simplest modulation. We can say full bridge based isolated DC-DC converter, we can say that's the most apt. So let us see the first simplest operation, where in my DTS by 2 period I will turn on my S1 and S4 switch simultaneously. That means I am just turning on this S1 and S4 switch together, and it has, if you look very carefully, this converter has two identical half bridges. These are one half bridge and this is another half bridge, and from the pole of half bridges we have connected the primary winding of this converter. The secondary part is similar to that of our push pull converter. Instead of this we could have also done ns number of turns. We could have done a simple full bridge rectifier, then C and RL. Similar to that we can do that. Instead of this rectifier power stage we can just use this particular the full bridge based rectifier instead of midpoint based rectifier. Now if you look very carefully, here we have DC, and because of switching of these switches we are actually injecting a high frequency AC at the terminal of this primary winding of this transformer, and on the secondary side we are actually rectifying it and then applying it to the LC filter, which is again having the same same kind of architecture as that of the push pull, and that it is also, we can say that it is nothing but the derived buck converter topology kind of. So now if you look very carefully, let us see how this particular converter operates, and it is called full bridge because we have used two half bridges to make them work like a full bridge. So in this case we are simultaneously turning on S1 and S4 switch. Since we are turning on simultaneously S1 and S4 switch, we are actually applying, if we define this as V primary voltage, so from the V primary voltage we are actually applying nothing but my V in voltage, this S1 turns on, this S1 turns on and S4 turns on. That is when we are actually applying the V in voltage across the primary winding. Since we are applying positive voltage across primary winding, this side will now have Ns by Np into V in, this Vp is now V in during dTs by 2 period. And because of that, what happens is that this dr1 will get forward bias, and since here again also we have n plus minus ns by np into V in voltage applied, this is now reverse biased, and then across L we are having IL current. So VL is nothing but is ns by np, we can write as n, so it is nothing but n V in minus V naught voltage applied across this inductor. And since there is a positive voltage applied across inductor, there is a positive slope of this thing, which is nothing but n V in minus V naught by L. And since we are applying a positive potential across the primary winding, so the flux in the core will start rising linearly, because V is equals to n d phi by dt, V is constant, n is constant, so d phi by dt is constant slope curve. So we will start from minus phi m and it goes to plus phi m with the slope nothing but same as that of V in by Np. And if we see very carefully, in this IL current we have the average value of this IL current is actually flowing through the load RL, while there is ripple component of that ripple component is actually going through this capacitor IC, and that is what is drawn here, that only the ripple part of that is drawn along the IC current. And since my S1 and S2 switch is on, we are just having 0 voltage applied across both the switches. Then in the next 1 minus dTs by 2 period, what happens is that in 1 minus dTs by 2 period, S1 S4 is off, and since the S2 and S3 is already off here, S2 and S3 is off here, and here also S2 and S3 is off. So we can say that since all the 4 switches are off, we can say that this is off, this is off, this is off, and since all the 4 switches are off, if we assume that each switches has some output capacitance, let's say C1 and C2, which comes because of the construction of the devices. So this C1 and C2, the voltage will be appearing since all the 4 are off. So the voltage in this part to this part will get equally divided among C1 and C2, similarly among C3 and C4. If in ideal case, if C1 and C2 are same and C3 and C4 are same, so the voltage which is applied at this point is V in by 2, and here also V in by 2. So actually there is no voltage which is been imposed upon the V primary, and that is why we will see the V primary voltage is equals to 0 since all the 4 switches are off. And since it is voltage applied is 0, the current which is going through there has to find a pathway. So they will find a pathway going from top winding and bottom winding, and since both because of that both the diodes will get forward biased, and that is when you will see that the DR1 and DR2 is on, that is when secondary windings is completely short circuited. So that is why we can say that we are now applying plus phi m, or we are, since short circuited, then d phi by dt is equals to 0. Since my d phi by dt is equals to 0, the phi will remain be the same at phi m. And since it is the this both are forward bias, if you apply a KVL in this particular loop, we will get VL to be equal to minus V naught. This voltage which is coming will come across this inductor, directly coming across this inductor, and that we will get in 1 minus dTs by 2 period, the same thing. Now in the next dTs by 2 period, what happens is that S2 and S3 is on while my S1 and S4 is off, is already off. Since my S2 and S3 is on, so we are now applying, if you see this one, we are now actually in this loop, and that's why we are now applying from V in minus V in voltage. And since we are applying minus V in voltage from Vp, we are actually here on the secondary side, we will see that our this potential is minus n times V in, and here it is minus n times V in. That's when you are now actually applying negative positive, this is NV in voltage, and that's when you will see that your DR1 gets reversed bias while your DR2 gets forward bias, and because of that the IL will be flowing like this, coming back here like this. And that's when we will see that the voltage applied across inductor, if you take the KVL in this one, minus NV in plus VL, and then it is plus V naught, so that will nothing but VL equal to NV in minus V naught, voltage applied across the inductor L. And again if we see this one is minus V naught by VL, and this one is nothing but NV in minus V naught by L. And then the ripple which is there will actually be flowing through the IC, so that's why we have rising ripple. So we have rising ripple, in previous duration it is falling, so this falling part is actually going through the IC, while the average value is actually going through the load resistance. And if we consider the previous case, we have missed one point in 1 minus dTs by 2 period. Since my S1 and all the 4 switches were off, and the C1 and C2 were blocking the half the voltages, that's why they were having V in by 2 voltage. If we assume both the switches to be identical, in this case, since my S3 and S2 switch is on, so the entire V in will be appearing across S1, and in the second half bridge it will be appearing across S4. That's when the Vs1 and Vs4 is nothing but V in voltage. The voltage applied across the Vs1 and Vs4 is nothing but the V in voltage. So if we look very carefully in this converter, we have to size our devices for only maximum up to V in voltage. That's one advantage with this converter. Then if we see very carefully in 1 minus dTs period by 2 period, in that 1 minus dTs by 2 period, we will see the same phenomenon will be occurring, where what we will see is that our S2 switch and S3 switch is now off, and all the 4 switches are off, because already my S1 S4 is off, and we can say that S2 and S3 is also off, is also turned off. Since they are turned off, what happens is that same thing will happen, the zero potential applied across the primary, and this inductor has to find the current, the inductor current, output inductor current has to find a pathway. That's when it will start applying through the top winding and the bottom winding, and that's when both the diodes will get forward biased, and then the half of current will be divided into both the windings, and as a result of which what happens is that from the inductor in this particular loop, if we do, it is just the VL is nothing but minus V naught will be applied across the inductor. And in during that period, since I have all the 4 switches are off, and we assume that the switches are quite identical, so the voltages will be appearing across their output capacitance equally. That's when we have V in by 2 voltages which will be appearing across all the 4 switches, and that is the thing we will see. And since the voltage across inductor is minus V naught, the inductor current is having negative slope of minus V naught by L. So we will see falling inductor current, and the constant average value will be going through the resistance, while the ripple value will be flowing through the capacitance. So this is how we will see that we will get this particular analysis, and when we do the And here also, if you look very careful, just like in case of push pull, the inductor will see the ripple component, which is nothing but 2 times of the switching frequency, because in 1 TS duration, if this is the your entire TS duration, the inductor current repeats itself after every TS by 2 period. So the inductor ripple frequency is nothing but twice the switching frequency, and that's when we have to size our output inductor and capacitance to twice the switching frequency component. So the L and C has to be sized for 2 FSW. That is one advantage we will get with this kind of arrangement. Since the inductor current repeats itself after every TS by 2 period, so we will now apply the volt second balance in TS by 2 period. So we can now write, V in minus V naught applied over dTs period by 2 period plus minus V naught applied over 1 minus dTs by 2 period, and it is equal to 0. That will give me value V naught equal to n V in times D, which is what we got in case of forward as well as push pull converter. However, here if you look very carefully, the flux is going from negative to positive phi m. So that's when we are now utilizing the core fully. And also if we look very carefully, the switching frequency or the frequency for which the inductor and capacitor has to size has to be 2 FSW, or you can say the inductor, the ripple component in the inductor is twice the switching frequency, and the voltage ripple across the capacitor is also twice the switching frequency. Now let us try to find how we can size the capacitor. Now if you look very carefully, in our previous discussion we have seen that this inductor current ripple component which is going through the capacitor, this value is nothing but delta IL, because the ripple component is flowing through the capacitor, this one. So now let us try to see the simplest thing, which is how we can size our capacitance. So this delta IL is only the ripple component of inductor current, which is an AC current goes between maximum ripple value in positive and in negative direction. Now this ripple component of IL is flowing through the IC. So let us try to see the sizing of capacitance C. Now if you look very carefully, the C will have the ripple, let us say the C voltage across C is nothing but delta V naught, the ripple voltage is delta V naught, and that voltage is actually, you can say that that is the amount of charge which has to be taken out or taken in from the capacitor, which will give us this delta V naught. Now in this curve, if we try to calculate our charge, so at this time our charge gets into the capacitor, and in this time it comes out of the capacitor this much amount of charge. So we can take the area under this curve, this particular triangle. So we will get the area which is nothing but, since it is a triangle, this value is nothing but going from this to this is nothing but delta IL by 2, and this delta IL is from this point to this point. If we try to draw delta IL, it is from this point to this point. So delta IL by 2 is in one direction. So it is half, we can say delta IL by 2, and into this period. This period is nothing but, if this is entire TS by 2, this is actually nothing but TS by 4. So we can say into TS by 4. So we can write the C value to be our delta IL by 8 to FSW, where FSW is equals to 1 by TS in delta V naught. So now this is, if you take our circuit, so this C has to be greater than this, I mean if we define this as C critical, so this C has to be greater than C critical. This value, if you look here, this value delta V naught is given in specification, how much amount of ripple you can sustain. FSW is the designer's choice, okay, and delta IL is something which you will allow the current ripple, generally 5 to 10% of I naught. So that can be easily, using this we can easily size our capacitance value in this full bridge converter. So let us try to see how we can size our inductor as well. If we look very carefully in this one, in 1 minus dTs by 2 period, we are applying minus V naught. So we can write that minus V naught is to be nothing but equal to L delta IL by during time t 1 minus d Ts by 2 period. This we can write, because we are applying in 1 minus dTs by 2 period, we are applying VL equal to minus V naught. So thus we can write this one, and then we can write L to be V naught 1 minus d, V naught 1 minus d divided by this Ts, we can write 2 FSW, and this one is, and this delta L we can take it at bottom side. And here if you look very carefully, this minus sign we are just, that minus sign we can neglect, because here the delta L will be negative as it is going from maximum value of ripple to minimum value of ripple. So we can just take the magnitude or modulus of V naught, as on the right hand side also we have taken only the magnitude of delta IL. So that's when we can rearrange and we can write L value in this way. And this V naught, we know that V naught value is nothing but N V in D 1 minus D divided by 2 FSW delta IL. If we look very carefully in this term, this is generally 5 to 10% of I naught. This is designer's choice, and depending upon what could be the output voltage, we can calculate this D depends on output voltage, and number of turns N, and this is again designer's choice. N is designer's choice, and this V in is given in the specification. Why I am saying designer choice? Because depending upon what will be the V in and V naught number of turns, accordingly we can design that particular thing. Now, so we understood how we can size our LNC. In both LNC we see that we are designing it for 2 times FSW, and that is why we can say that this LNC has to be sized for the frequency corresponds to twice the switching frequency. Now this is the operation where what we are doing is we are turning on our S1 and S2 simultaneously for DTS by 2 period, and we are turning on our S2 and S3 for DTS by 2 period, and in 1 minus DTS by 2 period all the 4 switches we are turning it off. Now if you look very carefully, we can also derive the same thing, another kind of converter, which is nothing but the half bridge converter, which is the performance, the most of the things will remain be the same. Let us define the half bridge converter. In half bridge converter we have input voltage, we have S1 switch, S2 switch. Instead of having two half bridges with switches, we can just have one half bridge with switches and one half bridge made up of capacitors. You can have C3 and C4, and then midpoint we will take this one on the other side. If we just see this one, on the other side we have this is NP, this is NS, diode DR1, diode DR2, so this way. RLC, and this is connected like this. Now if you look here, we have V in voltage and output is nothing but V naught voltage, and when we turn on here, in this case my S1 is on, and in this case my S2 is on. And if you look very carefully across the C3 and C4, we have V in by 2 potential, V in by 2 potential is coming over here, and then if we look very carefully in this circuit, whenever we are turning on S1 switch, so when we turn on the S1 switch, the V in potential is coming over here, and in this loop, if we turn on this switch, then in this loop we will get the potential, Vp during dTs by 2 period. My Vp is nothing but equal to V in by 2, this V in minus V in by 2, which is nothing but V in by 2, which is applied across the Vp, and that V in by 2 will be coming across this one here, and if we say Ns by Np to be equal to N, so it is nothing but N V in by 2, and that will be appeared across this inductor, same operation as inductor, and this inductor, this VL is nothing but my N V in by 2 minus V naught, if we do in this loop. Now in the next time when already my S2 is off, and when I turn off my S1 in 1 minus dTs by 2 period, what happens is that across this one there is a output capacitance of this switch, so they will also be blocking this Vn by 2, and they are also blocking Vn by 2, as a result of which the voltage applied across this is 0, and since the voltage is 0, so what happens is that on the other side we have the current IL going in, this goes down on this side and this side, and that's when we can say in 1 minus dTs by 2 period, it is nothing but VL, voltage applied is nothing but minus V dot, same as what we have seen in the full bridge case, we are applying minus V naught. Now and then if we do the same analysis, our second balance on L, if we do voltage across L, we do that, we will give V naught to be equal to N V in by 2 D. How we will get? We can write here, N V in by 2 minus V naught dTs by 2, and then minus V naught 1 minus dTs by 2 period equal to 0, and when we will rearrange, we will get V naught equal to N V in by 2 D. And since when we turn on this S1 switch, we are actually applying V in by 2 from the primary winding, so that's why we have V in by 2 Np. With that our flux will be rising, it reaches plus 5 m, and then when my S1 switch is off, my S2 is already off, so here S2 is off, S1 and S2 is off, here my S1 is off, S1 and S2 is off. So during that time both the S1 and S2 is off, the Vp applies 0, and that's when the current will be distributed among the two windings, and that's when we can say that these two windings are short circuited, Vp is equals to 0, that's when my d phi by dt is equals to 0, that's when my flux is actually constant term, which is plus 5 m. And since that the current, because of that my VL applied is minus V naught, the current will be falling down, here it is N V in by 2 minus V naught by L, value it is going down, it is minus V naught by L, it is falling down. And when we will see, whenever my S1 switch is on, the voltage is 0 across S1 switch. When my S1 switch is, during this time when it is off, the capacitor of this device, the output capacitor of the devices will have the equal voltages applied across them, which is nothing but V in by 2. And whenever the S2 switch is on during another next dTs by 2 period, the entire voltage will be coming across S1, and that's when S1 has to block V in voltage. So it is similar to that of the full bridge, except two things. One, the output voltage is actually reduced by 2, because we are now using just one half bridge, another half bridge is made up of capacitor, series connected capacitor. So we have reduced the DC bus utilization, or you can say the DC utilization by half the voltage. However, we do not now use 4 switches, we just have to use just 2 switches, and 2 series connected capacitors. So this is all about full bridge and half bridge converter. This full bridge converter, when both the S1 and S4 switches are operated diagonally, together, and S2 and S3 switches together diagonally. So we will see you in the next lecture. Thank you.